Hey everyone, today we are putting a hole in our building to show you. Just like this, we're going to have a staircase that is going to find 2 points right next to each other, and then it's going to make a hole all the way to the ground level, but not remove anything from the ground level itself, and put a staircase in. We can now get to the top of the apartment complex. No matter how it is positioned or where it is generated, it'll make sure that it has all the room it needs to place the staircase and not get in any way of any of the floors below. So if there was going to be a wall that was going to intersect with it, it is going to go ahead and make sure that it is removed before intersecting. As you can see like here, it has removed the wall in between, so that way it can place this. So today I'll be showing you guys how to select 2 points that are adjacent to each other in any configuration. So for this process, we're going to be making a custom Unreal node, and I'll go ahead and start from scratch. So that way you guys who might not be with us from the beginning of this series can follow along and create this node for your own project as well. Let's get into it. So to get started, I'm just going to grab ourselves an execute blueprint node just in our PCG graph, and I'm just going to pick a random one of these nodes and navigate to it. That way I just go ahead and open up the engine content where all these nodes are. And I'll go ahead and just duplicate the set point color node. I'll duplicate it and I'll call it something like 2 points. And I'll go ahead and move it into our PCG folder so we can start working with it and open it up. So here in our node graph, and to get started, we're going to go ahead and double click on execute with context. And this is our execution graph. This is our main graph where we're going to be doing everything. So let's go ahead and kind of clean this up from the get-go. We don't need some of the stuff. For example, we can go ahead and kill this point loop, this target actor, and this target actor. Get rid of all of this. And then we can move this down. And we can go ahead and remove this point loop body. And double-click on node title override. And this is our name. When you drag it into our PCG graph, this is the name that appears in that graph. So if we go ahead and call this 2 adjacent points, and if I was to compile and save this, if I just drag it in like so, you can see it's now called 2 adjacent points. So let's go back to our graph, and let's also open up our class defaults, and in category instead of color, we're going to put it under custom. So that way, when you compile and save this under custom, you'll see all your custom nodes that you've done. You can see I have already created a node in the past. That's why I have a testing node here. But of course, here's our new node that we have created. So I'll go ahead and just take this and just move it over down here to get it out of the way. We'll need this stuff later. And I'm going to drag these 2 nodes to the right, and I'm going to promote tags and pin to local variables. And I'm just going to call them as they are, tags and pin. And I'll go ahead and just set them right in this line. So that way I can use these over here at the end. And this is just to make sure that if there are any tags or pins, that they get kind of all the way down the chain and they'll end up where I need them to be. Great. We're not doing anything with tags and pins in this current matter, but if I was to reuse this node down the line and it did contain tags or pins, I want to make sure that it retains any information it had have before. So from here, we'll go ahead and just move this over to clean it up. And not to have this line going all the way from the beginning, I'm going to right-click, click Get in Context, and I'm going to plug that into the context. And then I'm going to promote this point data with context. I'm going to right-click and promote it to a local variable, and I'm going to call it PCG point data, which is literally what it is. As you can see in our local variables, it is PCG point data, which is why I just named it exactly that. We're not going to have any other kind, so this works for me. Then from here, we're going to get points. And you want to get the plural one, you want to get multiple points, and we're going to promote that to a regular variable. And this is going to be our PCG points. So effectively, from our input, we're going to go through all the inputs. In our case, there's only 1, and we're going to get all of the points from that input in here. So now we're able to play around with this array of points any way we want. So just like in the previous times, what I want to do is start with a kind of a clean slate. So no matter what I've brought into it, I want to make every single point 0 density. So that way, every single point is black. That way, I have a nice clean slate to work with. So what we're going to do is grab our PCG points and do a for each loop. And then if we grab our PCG point, we can set array element. And if I drag out of item to make it my life easier, I can search for set, and then I can get set members in PCG point. So I can go ahead and plug this directly in between the two nodes. So what we're going to be setting is the array element, which can go into struct ref, struct out goes into item, and our array index goes into index. So everything here is pretty straightforward. And then in the set members, we're just going to set the density of everything to 0. So all it's going to do is go through every single point, set its density to 0, and then save it to the array. From this point, we want to select a random point where we're going to have our staircase. I don't actually want to have it in a very specific place. I want it to be a completely random location inside of this building. From our complete node, we need to grab our PCG point, and you can do this one of two ways. You can either get a random array item, which will get us the random point. But what I've noticed is this is not quite as random as I would like, and it's probably tied to the PCG in some way. So what I like to do is get the length of the array, and then from the length, I get a random integer, and this is going to be our index of that integer. So from our completed, I'm going to right click and promote it to a local variable, and this is going to be our random point index. And from our completed, it's going to go ahead and plug in here. And then what I can do is grab our PCG points and use a get node, and I'm going to get the index from here. And then I'm going to store this as a variable, a regular variable, and this is going to be our random selected point. And the reason I don't plug the value just directly in here like so is because I'm planning to use this index down the line, and if I have this plugged into two locations, it will randomize a different number in both locations. So I want to store it to make sure this number stays of whatever it is. But now that we have selected the point, this is where we're going to have to start spawning things. So I want to make sure that this point that we've now selected is going to be of a density 1. That is our baseline. So what I'm going to do is take this, and I'm going to duplicate it over, and I'm going to plug this in directly. The random point can go right into struct ref, and the density will just change to 1. So it's going to go through every single point, set them all to 0, pick a random one, and make that point 1. From here, we need to go through every single point and see if we have an adjacent point. If we do, great, we can continue on. If somehow it has picked a point in your configuration where there is no adjacent point, then it needs to re-loop on itself and find another point. So what we need to do is grab our PCG points and do a for each with break, and then it's going to need to figure out if it is adjacent, then it is going to branch. So let's go ahead and make that branch function. I'll break our array element. I can right click and go collapse to function right away. I'll make my life a lot easier, and I'm going to call it find adjacent point. And this can be a pure function. So let's get open it up. Here's our function. So we're going to need a return node, of course. Do I plug that in? So effectively, we need to figure out if the point that it has chosen is similar to the point that we have. So I can grab our random selected point, and I can break it to get the same information between the two. And then I can split the transforms. That way we have access to the locations of both. So effectively, we need to see if it is next to it. So what we need is to get a new variable in here, and we need a variable called wall size. So this variable is going to be a float, and it is going to be exposed. Because depending on our wall size will depend on how far the points are. So if I compile this, I can set the default value in here, and I'm going to set the default to be 300, and the slider min and the value min will be 0, so it can never go into negatives. And effectively what we need to do is, if this value plus or minus the transforms that we have is equal to a point that it has selected, then return true, otherwise return false. So what we're going to do is get ourselves an add node and a subtract node, and we're going to do this twice. So 2 add nodes and 2 subtract nodes. And on the second pin, we're going to split it so we have access to the individual axes. Now our setup is a grid, as a flat grid. So it can be either in X or in Y, and it can be positive or negative, which is why we have 2 positives for X and Y and 2 negatives for X and Y. So in our wall size, we go ahead and plug it into X for the first one, Y into the second, and X to the first one, and Y into the second for both the positives and the negatives, like so. And now we just need to compare it. Is this point that we have gone through in our array of points, is it equal to this point? Is it equal to this point? Or this one? Or the last one? Now this bottom value here is the approximation of how close is it to be correct for it to return true. I don't want to leave it at pure 0, so I'm going to put in a relatively small number. As long as it's within 10 units, I say this is going to be fine. You can, of course, pick a smaller number. You can pick 5, 3, but it's good to have some kind of buffer room. So that way, if the numbers are just not quite lining up, then it should be close enough and it'll pick it. We are not using very small numbers in our grid, so this will be fine because our walls are about 300 units, 310 units. So if the units were like 10 units away, if every single piece was 10 units away, I wouldn't use a 10 here. I would use like a 1 or like 0.5 within the range. But because our wall sizes are pretty large, I feel like 10 should be fine. So from here, we can go ahead and just get ourselves an OR Boolean, because effectively we can add 4 pins. And as long as any of these are true, we'll say that this is true. So I'll go ahead and plug all of these in. And here, I'm going to drag this OR pin right into the return node. And now we have our setup. Now, I also, from this, can figure out what direction we will need to turn the staircase to fit this configuration, right? Because if the point that we have selected is up, it needs to face upwards. If it's faced down, it needs to face downwards, left and right. So depending on which point it has picked, we need to rotate that original point where it is placing the staircase to face it. So what I'm going to do is actually also return all of these. So I'm going to return all 4 of these. I'm just going to drag them out right into the return node. And I'm going to just rename them as to what they are. So the first one is positive, and I've plugged it into X. So I'm going to call it pos X. The second one will be pos Y, and negative neg X and neg Y. So there we go. So now we have all of our options here configured. So now we can go back to our execute with context, and you can see here's our node. I can plug in our return node right in here into our branch. So assuming that this is true, we can now do our stuff. So from here, what I'm going to do is actually promote all 4 of these to a variable, and I'm going to promote them all to local variables. And I'm just going to call them what they are. So I'm going to call them positive X, positive Y, negative X, negative Y. And the only reason I'm doing it here and instead of inside of the function itself is just so I can have these as local variables instead of as global variables. Okay, so from here, we have found the point that matches. It has agreed it matches. So now we need to go ahead and set the point. So I'll go ahead and grab our set members and set array element, and I'm going to duplicate it over, and I'm going to plug this in here. Our structure reference is going to be our array element, so you can drag it over. And our index is going to be our index from the array. Now the density, we don't want to set this to 1 as well, like we did the original point, because effectively what we're doing is we need 2 points that are going to remove the area, but we only want 1 point to spawn the staircase because the staircase itself is 2 units wide. So we want some kind of discrepancy between them, but not a big one. I'm going to set this to 0.9 instead of 1. So effectively we're going to have 2 points. One is going to be 1, one is going to be 0.9 right next to each other. And once this has gone ahead and found the point, it has set it, we just need to add a new variable. I'll add a local variable. And this is going to be a Boolean. And I'm just going to say point found. And once it has completed this, I'm going to set point found to true. And then I'm going to loop this point found all the way to the break node of the for each loop. And I'm going to add some redirects here just to clean it up. Because once we have found a point, we don't need to go through this loop again. We can go ahead and kill it early. We're golden. So from here, we need to go ahead now and go through the points and rotate them according to the information that we just got. So I'm going to get our PCG points, and I'm going to do a for each loop, and I'm going to go ahead and break it to get our information from here. I'm going to split the transform because we're going to need access to our scale, location, and rotation because we're going to be rotating it. And we're going to grab our set members and set array element from here and duplicate it down. Plug this in here. And instead of density in our set members node, I'm going to uncheck that and check on transform and then split our transform. The location will stay and our scale will stay. So you can just plug those in directly. Our array element from our for each loop is going to our struct ref and our index is going to index as we have done before. The difference is going to be our rotation. So I'm going to split the rotation. The X and the Y rotation is going to remain 0. We only want to rotate it around the Z. So we're going to use our new variables that we have set up. We're going to drag off from Z and we're going to grab ourselves a select node. And we're going to select float. And we're going to say, if it is positive X, then go ahead and rotate it 90 degrees. If it is not positive X, go ahead and just double check if it is positive Y. If it is positive Y, rotate it 180 degrees. And if it's not that, our last check will be if it is negative X. And if it is negative X, it'll be negative 90. Because if it's negative Y, then it is at 0 degrees and we're good. So this is not the cleanest setup, but it does work. I haven't figured out a better solution to do things of this nature, these kinds of chains. If you do have suggestions for this, please let me know in the comments below. I would greatly appreciate it. Once we have this, we actually need something in between here that I did forget to put in. And that is we need to check if it has found a point. So from the completed node, I'm going to see if point found is true or false. So I'm going to add a branch node and I'm going to move this completed to true, as though if it has found a point, it will do the rotation. But if it has not found a point, so if it has gone through all of this, it has not found a point, then it is going to go ahead and go back over here, reset the points and start again. So I'll go ahead and just kind of clean this up a little bit. Assuming that it has found the point successfully, then you can do the rotations and continue on. But at this point, we can actually test it out already. So if I go back to where we had this add node here, and I just grab this and drag this over, let's go ahead and finish this up. So I'm grab our PCG points, and we're going to also get the PCG points data that we've made before. And if you're wondering how I'm getting this get node right away, if you hold Control, you get a get node. If you hold Alt and let go, you get a set node. That's how I do that. But you get the PCG point data, and then you can search for set points, and you can plug in your points. So from our completed, we're going to plug this in. And from here, we go ahead and plug it into this add node. And for our data down here, we grab and the same PCG point data, and we can plug this in here. So now we can compile and save this and test it out. So if I was to go ahead and just plug in our spline sampler directly into here, and then sample it, let's go ahead and change the number of floors we have to 1. And for the time being, I'm going to detach the generated room wall so I can more easily preview this. So from here, this to adjacent point, I'm just going to get myself a density filter, and I'm going to plug this in and sample that. And you can see there's our 2 points. If I scooch it over and regenerate them, there's our 2 points. One is 1.0 and one is 0.9. But you also always see they're 2 right next to each other, which is exactly what we want. Okay, so now that we have 2 points, we need to propagate them upwards, right? So we have multiple floors. We need to get them up, up, and up. Because right now, it's only on a single floor. Let's go back to our 2 points graph. So we need to check if the amount of floors is greater than 1. But if you have one single floor building, you actually don't need to do any of this stuff, right? We don't need a staircase going up to the roof. Now, maybe you guys would, but in my case, I'm setting it up where I do not have a staircase going all the way up to the roof. If I want one later, I can go ahead and add it in, but for the time being, no staircase to the roof. So what I'm going to do is at the very beginning, before it even does this setup here, I'm going to select all this, I take all this, and I'm going to just drag to the left, and I'm going to say, is the amount of floors greater than 1? And I'm going to get ourselves a branch node, and if it is true, then it is going to continue on. And we do want this floors to be exposed, so that way we can plug this in directly. But if it is false, we basically just can exit out of here. So I can just take this if I want. I can just duplicate it up here, plug this in, and it'll basically just exit itself out. But assuming that it is now in this loop, there's now more than 1 floor in this scenario. So we want to extend it. Now we want to extend it upwards, but we don't want to extend it the full length of every single floor, because the final floor, like the ground level, we don't want to put a staircase up. onto it because we want to, again, not have it go up to the roof. So we want to do the max amount of floors -1 to eliminate that. But we also want to have an option to, on the ground level, when we're removing all the, making all the holes for every single floor, we don't want to remove the ground level's floor. This can be done in a multitude of ways. You can make separate nodes that does that, and then use one node in one scenario, one node in another scenario. What I have found is I just have figured out that for me, it's easier to set different density values for all the different types of nodes and scenarios, and then filter those nodes inside of our PCG graph to better utilize them. So that's what we're going to be doing. Now, if this has been helpful for you guys so far, I would appreciate it if you guys hit the like button. It helps me out a lot. And while you're down there, consider subscribing if you haven't for more awesome tutorials like this. Let's get back to it. So now, instead of going right into the set points completion, now scooch this to the left, we need to move and copy these points upwards. So from here, we're going to grab our PCG points and do another for each loop. And I'm going to grab our set members and set array element. I'm just going to duplicate it over here. I can recombine the rotation, so keep that as is. Now, before I plug this in directly, what we're going to want to do is store this information into a new variable, and then we're going to recombine them at the end. So what I'm going to do is add a new variable, and I'm going to call it just PCG points collection. And the type is going to be PCG point, and it is going to be an array. So effectively, we're doing the same thing as our PCG points. This is just going to be a new collection. So we're going to want to is add our PCG points to this loop. Now, we don't want to plug this in directly. And the reason we don't want to plug this in directly is because, as I mentioned earlier, the first floor, we want to actually have that be different. We don't want the values of the first floor to be 1 and 0.9, like the second floor and third floor and fourth floor, because if every single floor is the same values, we can't separate it out. So what we're going to do is take our array element, and we're going to break it, and we're going to split our transforms, because we're going to need that. But effectively, what we need to do, from this add node, we can search for set members in PCG point, plug in our loot body in here, and then this into the add node, and we need to be setting the density. So we're going to be controlling the density from here. And we're going to need kind of a bit of room. So I'm actually going to take all this and just drag it over to the side. And from our density node, I'll go ahead and grab ourselves a select float. And what we need to see is if it has completed any of the loops. So I'm going to add ourselves a new local variable. And the local variable is just going to be floor passes completed. It is going to be a integer and is going to be a single. It's not going to be an array. And by default, it is actually going to be 1. And you will see why shortly. So from here, you can go ahead and grab the floor passes completed. If it is equal to 1, then it will pick A. So if it is the first floor, then it will pick A. So if it's the second floor or on, it will pick B. So we can grab our density and plug it into B. For A, we need to see which point it is. So by getting ourselves another select float, we can get our density and we can say, is it greater than 0.5? You can use any number that's not 0, basically. Is it greater than 0? You can even leave it as that. But I like to just be safe and just put it a little bit of a higher value. And basically, we're checking if it is one of the 2 points that we have selected here. If it is not, it is set as 0, as we have gone through the entire loop and set them all to be 0 previously. So again, you can just leave that at 0 if you would like. So if it is indeed a point that we have chosen, it'll go A. Otherwise, we can leave the density as it was. So you can plug B back into there. So for A, what we're going to do is just take our density, and we're going to subtract 0.2 and plug that into A. So our 1.0 will become 0.8, and our 0.9 will become 0.7. So now we have more values to play with to isolate specifically the first floor. Wonderful. So let's go ahead and plug on our array element in here. Now we're storing the information from our original points with the correct density now, depending on the floor it's on, into this collection. So from here, we need to also move then the points up from this loop. So we go ahead and take our rotation. We can plug that in directly. Take our scale, plug that in directly. But for our location, we need to add And we can split the input pin and plug that into our transform. We need to add height. So we need to know our floor height. So let's go ahead and add a new variable. I'm going to call it floor height. It is going to be a float, and it is going to be exposed. By default, I'll go ahead and set this to 300 because we have it currently hard-coded for 300. Again, this will later down the line, we will adjust it so it'll be a variable. But I can go ahead and plug in our floor height into our Z. Once it has stored that information, it takes all the points and it moves them up. So again, I'll grab our array element, drag this into the struct ref, and I will take our array index and drag it over into the index of the set array element. Now we also need to, again, remove the topmost floor. So the way we're doing that is by exposing density on the set member node. And we're going to, once again, from the set density, I'm going to use a select node. So if it is going to be true, we're going to set it to be 0.5. And if it is going false, it is going to be our default density, grab from the original. What we're going to check is the density greater than 0.5? And is the number of floor passes completed plus 1 equal to the amount of floors? We're adding 1 in here because we want to stop it from going to the highest floor, and we're comparing it to the amount of floors we have entered. And the reason we're adding 1 here is because it is going through this loop right now, but it hasn't completed it technically. So we're assuming once it completes it, this number will be accurate. But for the time being, we're using it just within the loop itself. So assuming that these both are true, we're setting that value to 0.5. So now we have a value that is 0.5, 0.7, 0.8, 0.9, and 1 for all the different scenarios of all the different point types we have. But once it has done this, we can go ahead and set our floor points completed, and we can increment it by 1. So again, now this number will match this with its addition. So that's why we're doing it like this here. So at this point, we need to check if we have done enough floors. So from here, we go into a branch node, and we just check if the amount of floors is greater than the floor passes completed. If the amount of floors is greater, that means we need to continue doing this loop. So I'll go from true back into our execution pin. And from our completed, we also need to go into this execution pin. So I'll go ahead and just quickly reroute this just to be a little bit cleaner because it's going to get a little bit messy in here. It will keep going through here, re-adding the points, moving them up, re-adding the points, moving them up, always double checking the densities as it does. But once the amount of floors is not greater, that means it is completed, we need to just go ahead and go grab our PCG points collection. And for each of these points, we just need to add them back into our PCG points. So grab our PCG points, grab ourselves an add node, and we're going to plug them in. So it basically re-adds all the points back to where they were. At which point we need to exit out of here. So we can grab our return from here, drag it over, and plug this into our completed. Now in here, we need to plug in the amount of floors we have. So here, when you plug this in, it seems, oh, we still have the variable from before. We still have linear color. We can go ahead and remove that. We can delete that. That is from the previous node. We don't need that. So we can grab ourselves a floor node. So I'll grab ourselves a get actor property from here. So we're using it here. Just duplicate it over and plug this in. If you don't have one, just right click, get actor property, and you just want to plug in your variable name right into the property name. Wall size is 300. Now in our case, it's 310. And we actually have our wall size. So I'm actually going to duplicate this, plug this in, and I'm going to call this wall size, because that is what we have it here as named, wall size. So our wall size will plugged in there. Our floors is plugged in. Our floor height is hard-coded currently. So I'm going to close this up. And now you can see right here, we have 2 points and 2 points above, and then 2 points again, but these are 0.5 in value. So if I go ahead and just change the amount of floors to, let's say, 5 and have it regenerate, there's our 2 points on top. And if I go down, you can see the points are of different values. And I can show you these 2 points down below on the ground level are also of a different value. Now, if you guys have followed along so far, but for some reason yours is not looking the same way as mine is in the scenario, feel free to join the Discord. The links are in the description below. We'll be able to help you out there as well. Or if this is a bit too advanced and you just want to study the files themselves, we do have a Patreon where I am uploading all the project files there as well. And you can be like these lovely people down here and help support what I do. So thank you very much to them, and let's get back to the tutorial. Okay, let's start with removing the actual floors from all of these. So I'm going to go into our PCG blueprint, and what I can do is take this, and I'm going to move this kind of over to here. So I'm going to grab from here, and I'm going to need 2 density filters. So the first one is going to be 0.5 exactly, because 0.5 is the top level. We want that removed. And we want another filter, and that is going to be between 0.9 and 1. So it's going to be everything except the bottom floor. So if I go ahead and take these two and merge them, so it's one node, we can now use a difference node and cut this out. From here, I'm grabbing a difference node. And after this transform points, we're going to take that as our source. And this merge is going to be our differences, because that is what we're going to be cutting out. So I'm going to detach from this second transform points, and I'm going to plug this difference into here. And the final thing we need to change is on this difference node, we can change it from minimum to binary. And you can see if I stop sampling our density filter over here, we now have a hole in the ground. If I go unlit, you can see we have a hole all the way to the ground level. If I put a light in here, see, it goes all the way down, but it does not actually impact the actual ground level. Because again, we don't want something on the ground level. This is exactly what we want. Perfect. So we have every single floor cut out, minus the roof. And you can see if I plug the roof in here, the roof is still full, but we're turning off the roof for now. We now need to also cut away from the walls themselves. We don't want these walls to go through it, because there's a chance that the walls can cut through where the hole is. So if I regenerate a bit, you can see right here, we now got a wall in our hole. We don't want walls in our holes. That's bad. We need to go ahead and add ourselves a difference node up here before we take our points. So in our case, we want to kind of remove everything between 0.5 and 1. So I'm going to grab ourselves a difference node again. The generate room walls will be our source. The density filter from between 0.5 and 1 will be our difference. I'll alt-click to remove that connection. And I'm just going to move this down, kind of slightly organize this. And this output will go ahead and plug into our transform points. So now at no point will it actually ever have walls here. So you can see here it was going to have a wall here, but because the hole is here, you can see the walls have stopped. They do not intersect into this whole area. Wonderful. So that is now working as intended. So while we're here, let's add the staircase in. So what I have done is I've gone through the Megascans files, and I've just taken a few of the stairs, and I've made myself this setup here, where I just have a staircase with a slight floor, slight second floor, ground level, and a staircase. So you can go ahead and make yourself one of these. Of course, it'll be unique to however you want it to be designed for yourself, but this is what we'll be using in my case. And of course, if you were to grab the project files on Patreon, this is one of the files that's of course going to be available to you. So what we want to do is grab ourselves 2 density nodes. And the reason is we want to grab specifically 1.0, which is going to be our main point that is going to be on the ground, right? We have a 1.0 and a 0.9. We don't want to spawn 0.9, but we also want to spawn on the ground level, which is 0.2 below. So we want 1.0 and we want 0.8 specifically. So lower bound and upper bound will be 0.8. So by adding just a reroute node here, I can just make this a little bit cleaner. So I can grab all of these points kind of together. From here, I'll go ahead and merge these. So we have a nice clean single node. And then I'm going to grab ourselves a transform points and then a static mesh spawner. In the static mesh spawner, I'll go ahead and add ourselves a mesh entry. And this is where I'm going to plug in my staircase. And if I check out my model and I come over here, you can see it has added it, but it is kind of offset. Now this will depend on your model and the offsets you will need for them, depending on where your pivots are. So in my case, I'm going to go ahead and set this up as -100 in X and -155 in Y. And this is min and max will be the same. And now you can see it has lined it up. So if I go ahead and move this around, it lines up with the point. And if I come here and I just hold L and left click to add a light down, you could see that it goes all the way down. We can fly down here, copy the light, and there's a staircase on every single floor, as you can see, going all the way up to the highest level. And we don't have anything in the way between each one. So each one has a way of getting in here, and on the other side, a way of going up and down. Now, the only last thing I want to do here is fix up these kind of back faces. They're kind of unruly, so this is an easy fix if you don't have a two-sided piece of geo. So all I'm going to do is grab ourselves an extra transform node. So from our density filter, I'm getting myself a transform node. And all I'm going to do is scale them in -y. I'm going to uncheck uniform scale, and I'm going to scale them in -y and y. Now, depending on your asset, you might need to scale them in a different axis. And I'm also going to offset them by -50 in y. And that is due to the thickness and the pivot of where it is. So I'm going to take this and I'm going to duplicate it. And I'm going to do that for both of the interior wall pieces here. And I'm also going to do that for the exterior wall pieces. So over here, I'm going to duplicate it here. And same thing, just plug the in, out to our static mesh spawner. And once I've done that, as you can see, we now have two-sided walls. So there we go. So now I can go ahead and generate any amount of floors I want. So I can set this to be a very tall tower of 8 floors tall. I can regenerate it. We have a new unique layout for each one. And going down the entire length of the entire complex, we have a staircase that is 2 units wide. It is now all set up with interior staircase. And that's it. Later.